Hey there, science fans! Today, we're diving into the fascinating world of batteries, those little powerhouses that keep our modern lives running. From our smartphones to our electric cars, batteries have become indispensable. But have you ever stopped to wonder how these marvels of engineering actually work? A battery is essentially a device that stores chemical energy and converts it into electrical energy. It's like a tiny chemical factory that produces a stream of electrons, the tiny particles that carry electricity. This flow of electrons, also known as electric current, is what powers our devices. Batteries come in all shapes and sizes, but they all operate on the same basic principle: controlled chemical reactions. These reactions involve the movement of electrons from one part of the battery to another, creating an electrical potential difference that drives the flow of current. So, buckle up as we embark on an electrifying journey to uncover the secrets of batteries and their impact on our modern lives. Let's take a peek inside a typical battery to understand its inner workings. Imagine a battery as a tiny chemical reactor with two main compartments, the anode and the cathode. The anode is the negative terminal, while the cathode is the positive terminal. These two electrodes are immersed in a special chemical soup called the electrolyte. The electrolyte acts as a pathway for ions, which are atoms or molecules that carry an electrical charge. When a battery is connected to a circuit, a series of chemical reactions occur at both the anode and the cathode. At the anode, a chemical reaction releases electrons, which then flow through the external circuit powering our devices. Meanwhile, at the cathode, a different chemical reaction consumes electrons. This flow of electrons from the anode to the cathode is what we call electric current. To maintain the flow of current, the electrolyte allows ions to move between the anode and the cathode, completing the electrical circuit. This continuous movement of electrons and ions is what keeps our devices powered up. Now let's delve a little deeper into how the flow of electrons actually generates electricity. You see, electrons are like tiny magnets, and they have a natural tendency to move from a region of high energy to a region of low energy. In a battery, the chemical reactions at the anode create a surplus of high-energy electrons. These electrons are eager to find a lower energy state, and the only way for them to do so is by flowing through the external circuit. As electrons flow through the circuit, they bump into atoms in the wires and other components, transferring some of their energy along the way. This transfer of energy is what powers our devices, whether it's lighting up a screen or spinning a motor. Finally, the electrons reach the cathode, where they are absorbed by the chemical reaction taking place there. This process of electron flow continues until the chemical reactions inside the battery reach equilibrium, at which point the battery is considered discharged. Not all batteries are created equal. Some batteries, like the ones we use in our TV remotes, are designed for single use and are discarded once they're depleted. These are called non-rechargeable batteries. Rechargeable batteries, on the other hand, can be juiced up multiple times. These batteries, like the ones in our smartphones and laptops, rely on reversible chemical reactions. This means that by applying an external electrical current, we can reverse the chemical processes inside the battery, essentially restoring it to its charged state. The key difference between rechargeable and non-rechargeable batteries lies in the nature of their chemical reactions. In non-rechargeable batteries, the chemical reactions are irreversible, meaning that once the reactants are used up, the battery is spent. In rechargeable batteries, however, the chemical reactions can be reversed by applying an external current, allowing the battery to be recharged. This ability to recharge makes rechargeable batteries a more sustainable and cost-effective option in the long run, especially for devices that require frequent power. Section 5. Lithium-ion batteries, powering the modern world. Now let's talk about a special type of rechargeable battery that has revolutionized our technological landscape, the lithium-ion battery. These batteries have become ubiquitous in our modern world, powering everything from our smartphones and laptops to electric cars and even power grids. So, what makes lithium-ion batteries so special? Well, for starters, they boast a very high energy density, which means they can store a lot of energy for their size and weight. This is crucial for portable devices where every millimeter and gram counts. Moreover, lithium-ion batteries have a relatively low self-discharge rate, meaning they lose their charge slowly when not in use. This is why your smartphone can still hold a charge even after being left untouched for a few days. But perhaps the most significant advantage of lithium-ion batteries is their ability to be recharged hundreds if not thousands of times without significant degradation. This long lifespan, coupled with their high energy density and low self-discharge rate, has made lithium-ion batteries the go-to choice for a wide range of applications. Section 6. The lithium-ion revolution, from smartphones to electric cars. The advent of lithium-ion batteries has sparked a revolution in portable electronics. Thanks to their compact size and high energy density, lithium-ion batteries have enabled the development of increasingly smaller and more powerful devices. Remember the days of bulky cell phones with limited battery life? Those days are long gone, thanks in no small part to the development of lithium-ion batteries. Smartphones, laptops, tablets, and countless other portable devices have all benefited from the superior performance of lithium-ion batteries. But the impact of lithium-ion batteries extends far beyond the realm of consumer electronics. Electric vehicles, which are poised to revolutionize the automotive industry, rely heavily on lithium-ion batteries for their power. The high energy density of lithium-ion batteries allows electric vehicles to achieve impressive ranges on a single charge, while their fast charging capabilities make them a practical alternative to gasoline-powered cars. As the world transitions towards cleaner and more sustainable transportation, lithium-ion batteries will undoubtedly play a pivotal role. Section 7. The dark side of lithium-ion sustainability concerns. While lithium-ion batteries have ushered in a new era of technological advancements, it's important to acknowledge the environmental and social challenges associated with their production and disposal. The extraction of lithium, a key component of these batteries, often involves large-scale mining operations that can have detrimental effects on the environment. These operations can lead to habitat destruction, water depletion, and soil contamination. Furthermore, the manufacturing process for lithium-ion batteries is energy-intensive and relies on the use of various metals and chemicals, some of which can be toxic. Improper disposal of lithium-ion batteries can result in the release of these harmful substances into the environment, posing risks to both human health and ecosystems. Addressing these sustainability concerns is crucial to ensuring that the benefits of lithium-ion batteries do not come at the expense of the environment or human well-being. Section 8. Beyond lithium-ion, exploring alternative battery technologies. Recognizing the limitations of lithium-ion batteries, researchers around the world are actively exploring alternative battery technologies that offer improved sustainability, performance, and cost-effectiveness. One promising avenue of research is solid-state batteries. Unlike conventional lithium-ion batteries that use liquid electrolytes, solid-state batteries employ solid electrolytes, which are less prone to leakage, flammability, and degradation. This makes them potentially safer and more durable than lithium-ion batteries. Another area of interest is sodium-ion batteries. Sodium, which is abundant and widely available, offers a more sustainable alternative to lithium. Sodium-ion batteries are still in their early stages of development, but they hold promise for applications where cost is a major factor, such as grid-scale energy storage. These are just a few examples of the many exciting developments in the field of battery technology. As research progresses, we can expect to see even more innovative and sustainable battery solutions emerge in the years to come. Section 9. Towards a sustainable future: battery recycling and responsible sourcing. As we become increasingly reliant on batteries, it's imperative that we adopt responsible practices for their production, use, and disposal. This includes promoting battery recycling, reducing our reliance on conflict minerals, and supporting ethical sourcing of battery materials. Recycling lithium-ion batteries allows us to recover valuable materials, such as lithium, cobalt, and nickel, reducing the need to mine virgin resources. This not only conserves natural resources but also helps to mitigate the environmental impact of battery production. Furthermore, we must address the ethical concerns associated with the sourcing of certain battery materials, such as cobalt, which is often mined in countries with poor labor practices and human rights records. Supporting companies that prioritize ethical sourcing and transparency in their supply chains is crucial. By embracing a circular economy approach to battery production and consumption, we can maximize their benefits while minimizing their environmental and social footprint. Let's work together to ensure that batteries continue to power our world in a sustainable and responsible manner for generations to come.